So with that, I think we are ready to begin. Moselle, when you're ready, you can start.
Okay, thank you. Uh, so good morning. My name is Moselle. I'm currently a GIS analyst working at McGuire Air Force Base in New Jersey. My basic responsibilities there, it's a lot of data management across the three bases, military support and training, portal app creation and maintenance, and really anything else map related that comes up during the day. So today I'm presenting my capstone project, a spatial analysis of terrorist attack types and their patterns using the KOF index. The goal for this project was really to produce an analysis that explored how terrorist attack types spread at the country scale over time, the levels of information access as defined by the KOF index that I'll go into a little more later, and explain any changes in frequency associated with these patterns, and of course, to visualize the data. So the attack data is coming from the Global Terrorism Database, and the relative level of access to internet, a TV, the free press within a particular country is drawn from the KOF Information Index. There were a few goals and objectives I was trying to reach here. The first was identifying high density regions, and then calculating percent change, which is changing KOF growth for information access in countries that intersected these areas. And this let me kind of narrow down the country selection to just 5 countries to focus the attack type analysis on. I isolated one attack type per country just based on the most frequently used identifiable attack type. So anything that's not the top ones were usually unidentifiable explosion or unidentified firearm. Um, so the time increments to study change over time, I tried to focus on 10 and 5-year increments, 10-year increments before 1980, and then uh, before 1990, and then after 1990, I tried to focus on 5-year increments just to take into account just more rapid technology development over the past 20 years or so. There's been a huge amount of research on this topic, obviously, how and why terrorism spreads, an increasing number of studies on the relationship between terrorism, communication, and the internet. There's less research regarding distribution of attack types and the access to informational resources. This includes methods of distributing the practical knowledge base and success rate of an attack that could provide the impetus for terrorists to use one particular weapon over another. The current body of research indicates some debate about why terrorism is distributed or concentrated the way it is. Here you can see a few hotspots identified in a study in 2025 on different factors. So total attacks, number of fatalities, non-fatal injuries. But with these hotspots in mind, there's still a lack of clear consensus on how these ideologies and attacks spread. There's also little evidence that hotspots of terrorist incidents share any clear cultural profile, making some regions more susceptible to terrorist activity than others. And one other study noted that hotspots of terrorist activity uh, concentrate within 10-year periods. So only within a decade, only a few countries hold the majority of all terrorist attacks, and those countries kind of change from decade to decade. Moving on to strategic emulation and concentration. This is just referring to indications that attackers are often influenced by the attack types and successes of other incidents and other terrorists, and that these can be diffused worldwide depending on how widely publicized they are. And the authors attribute this mostly to diffusion through mass media. Strategic concentrations is the idea that one or two methods of attack are more common to a region than others. So, for example, infrastructure and assassinations are more common in Western Europe, but hostage taking is more common in South Asia and South America. So, there is a consensus that increased globalization and connectivity globally correlates with a decrease in the total number of terrorist attacks, and agree this could be due to online counterterrorism measures, but there is conflicting evidence on at the country scale or within different demographics. So in a study in 2020, the authors discovered that as information flows increase, So does terrorist activity, but only up to a certain point. So once countries cross the threshold, terrorist activity decreases again as the information access gets incredibly high. So looking at some smaller scale studies, just briefly. So one looked at the relationship between internet usage and ISIL recruitment in Tunisia. The authors found a correlation between increased internet access and the increased number of recruits. In another data set on UK-based terrorists, 61% of them had an online presence related to radicalization or attack planning. And then on a data set in the US on extremists and social media usage, 90% of those extremists were radicalized in some way by social media. So over 50% of them were radicalized with social media acting as either the primary or secondary role of radicalization. Another thing to note from that study is that the time it takes to radicalize is also decreasing. So moving on, I used two main data sets for this project. The Global Terrorism Database from the National Consortium for the Study of Terrorism and Response to Terrorism, or START. It's through the University of Maryland, and it covers over 200,000 terrorist attack points over a 50-year period, all collected from open source data. It covers information like location, weapon type, casualties, targets, group affiliations, if that's known, among a lot of other information. And then moving on to the KOF index, I'm actually using a sub-index of this, the Informational Globalization Index, that ranks a country's level of information access to the internet, TV, and the free press. Ranks from 1 to 100. So 1 is the least, and 100 being the most access you can get. And the timeline is over a similar period. So for this project, I'm capping it at from 1970 to 2020, just so it lines up with the Global Terrorism Database. The methodology was also in two sections. So I did a global point density analysis as well as an attack type analysis. So the global point density was kind of focused for the tessellation. It was just a data aggregation of all attack points, just seeing where the most high frequency areas were. Then the K function focused on regional and country concentration and dependence. For the attack type analysis, this was at the country scale and was over the lifetime of the attack type for that country. For the tessellation, this was just looking at frequencies for the attack types in that country over time. And then the SDE looked at the directional weight and orientation of points as well. So moving on to the results, starting with the point density and percent change analysis here. So these figures kind of show a comparison of informational growth variation globally in areas that contained these high frequency hexagons in darker green. So there's informational access growth across the board in all the countries looked at here, indicating a lot of variation in these attack dense areas. And a few things I wanted to note is that neighboring countries don't always appear to share similar levels of growth. So for example, Afghanistan and Pakistan have 87 and 110% growth respectively in the KOF index. And there's a similar relationship between Colombia and Peru. The lowest growth here is in Somalia and Nigeria with only 39% and 25% growth. And the highest being in the Philippines, Japan, and Spain. So the tessellation map on the bottom shows higher attack numbers in several areas. There's a large cluster around South Asia, the Middle East, Central and South America. There's a larger one in the Philippines. There's scattered points around the United States, some smaller hotspots in sub-Saharan Africa, and scattered points around Europe with kind of a larger hotspot in the UK. That's also one of the countries studied here. So the country selection. So I chose these 5 countries and the most common attack type that could be identified. This is based on the density of attack information over time, as well as regional and KOF growth variations. Each of these countries also has an identifiable attack type that spikes over the lifetime of the global terrorism database. So the K function showed overall showed very high dependence and concentration. I'm using South Asia as an example, as a representative example. So this is showing successful and unsuccessful terrorist attacks between 1970 and 2020. And you can see the curve is pretty high above the random distribution curve in red seen here. So all of the K function results I ran showed a heavily concentrated and dependent attack type data, regardless of location, success, failure, or type of attack I used to filter the data, as well at regional and country scales. So for the tessellation and SDE results, I'm using Pakistan as an example here. They had remote trigger attacks starting in 1998. So initially, they're pretty disparate hexagons, low frequencies. They start to concentrate in the north from 2006 to 2010, and then start to spread south, creating these smaller high density areas before attacks start to subside after 2013. There's a spike in these attack types in 2013, as you can see in the fourth map here from 2011 to 2015. For all 5 countries I studied, attacks were initially more dispersed, similar to this example, and then one or more isolated hexagons sort of became a hotspot, as you can see here in the north of Pakistan on the border with Afghanistan. From there, attacks spread to smaller concentrated hotspots, like outposts, kind of like from a main base of activity. But in some cases, these attacks appear to contract back into the original hotspot as the number of attacks declines. And it hasn't declined quite enough to see if that's happening in Pakistan here. The SDE analysis for Pakistan, you can see kind of similar results. The very elongated ellipse in the first 2 maps. The points are pretty spread apart. It contracts drastically in that first northern hotspot that pops up and then starts to move south as more kind of smaller hotspots pop up there. So from 1998 to 2010, the epicenter of these attacks shifted across the width of Pakistan. In the other 4 countries studied, the center of the ellipse remains relatively constant despite changes in shape or directional weight of the ellipse. So Pakistan's pretty unique in that case. But all 5 countries showed some level of variation in size and shape for their SDE. It would expand for more dispersed and low frequency attacks, which usually appeared as the attack type was introduced to the country, like it is here. The ellipse would then contract as a larger spot appears, monopolizing the weight of the attack data during that time period. This was seen in Pakistan, the UK, Nigeria, and the Philippines. But in Afghanistan, the ellipse continued to expand. For KOF comparisons, this is over the lifetime of the attack type studied in each country. Each country has a pretty different timeline for informational access growth. Afghanistan, the UK, and the Philippines show a pretty similar informational growth curve. Pakistan shows a large jump near the beginning of their timeline for remote trigger attacks. The most prominent difference here is the relatively low increase for Nigeria, where suicide bombings were introduced relatively late compared to the other countries' attack types. They were introduced in 2012. Nigeria also doesn't ever show a major jump in the KOF index. It's always kind of a gradual increase or decrease. But how does this relate to changes in frequency and distribution of attack types? So there's a few patterns I wanted to go over and discuss here. Firstly, a large jump in the KOF value appears to coincide with periods of higher attack dispersion and can precede increases in attack frequency. This is seen in the cases of Pakistan, as we looked at earlier, Afghanistan, and the Philippines seen here. In these countries, it's possible increased access to TV, internet, and the free press increases the range of certain attack types, but there are variations in how information access coincides with attack type data. And it's not the case for the UK or Nigeria. So in the UK, the KOF growth starts during a high concentration period. You can see all the attacks are concentrated in Northern Ireland. And in Nigeria, as we looked at before, there's very little growth in the KOF informational access growth across the lifetime of the attack type, despite significant variation in the spread and distribution of suicide bombings throughout the country. The Philippines also shows contradicting patterns. The KOF increased in a period of low concentration, relatively lower concentration and low frequency, as well as a period of increased concentration and higher frequency. The only difference I saw there is that the initial higher dispersion period is before the introduction of a lot of major information technologies, and the latter is afterwards. So basically, a lot of the big takeaways from this study, the main one is that patterns indicated show relationships between informational access and the rise of different attack types. In many cases, are unique to the country, though there are some similarities in several cases. There are many factors that go into the spread of information not studied here. Not least is language, culture, and geography of a region that either promotes or impedes the travel of information and ideas. So this project explored the spatiotemporal distribution of attack types used by terrorists at the country scale within different regions, focusing on the relationship between attack frequency, distribution, and information flows. One relationship didn't exist here. This study kind of reflects the snapshot into how the implementation of certain weapons was spread within countries over time. And my hope is that this kind of begins the process and provides a foundation for further research in this topic as information technologies grow ever more present and embedded in daily life. So this is my bibliography. If there's any questions, answer that now. Hopefully that was in the time.
All right, Moselle, thanks. Great presentation. If you open up the chat window, it looks like there's a question
Okay,
there
I'm
for
looking.
you.
On your early slide on spatial distribution, the concentration of non-fatal attacks in the US focused on the east and northeast portion and nowhere else in the US. Do you have any thoughts on why this is? Okay, let me try and go back to that slide. I think that's this slide. Um, so actually in the global terrorism database, there were a few like high frequency hexagons, and they were focused on I think it was around New York and then in California. So um, I'm not quite sure why this is, except that in a lot of, so most of the high frequency areas that I looked at really kind of focused around urban areas. Um, and the east and northeast of the US is pretty populated. So that's that's my guess on that. But everything I looked at, they were really concentrated around cities or just heavily populated areas. So that's thinking that's why that is.
I was wondering if you could maybe comment briefly. So the KOF index is, um, I take it, rather generic in terms of what it constitutes as information. Um, have you thought anything about maybe looking further into the different kinds of information and their impact? For example, like what influence did the arrival of cell phones versus social media versus the internet versus, so different kinds of technology and how that impacted information.
I definitely considered that when I was looking into this project. Social media was kind of a beast in terms of all the like previous research that kind of tried to tackle it. There was a lot of overall there was a lot of difficulty just like trying to pin down how social media was affecting um, anything. It's just really hard to track. So I think in the future that should be a major focus. Um, Sort of developing any kind of data set that looks in at how social media is really affecting uh, just the spread of different like strategies that people might use. Because oh, there's another question. Do mass shootings that are unfortunately common in the US get classified as terrorist attack in this database typically. Not in this database unless it's a non-state actor. So this START has a few different databases for terrorist activity. I think they have one for state actors as well. But this is primarily focused on non-state actors.
All right. Well, thanks again, Moselle, for your presentation. If you could put your email in the chat window in case someone wants to follow up with you, that'd be great.
Will do. Thank you very much.
And then next up, Freddie, if you want to go ahead and share your screen,
Will do. Thank you.
get that rolling here. All right, we see your presentation and we can hear you. So whenever you're ready, you can begin.
Okay, perfect. All right. Hello, my name is Freddie Aguirre, and this presentation summarizes my capstone proposal. My project focuses on identifying weather-related traffic crash hotspots in Montgomery County, Maryland. This research supports the county's Vision Zero 2030 action plan, which aims to eliminate serious traffic injuries and fatalities. Give me a second here. Sorry about that. Montgomery County has created a Vision Zero 2030 plan, which emphasizes a data-driven and equitable approach to road safety. Its analysis targets high injury corridors, but it doesn't specifically address how adverse weather may contribute to crashes. My project tries addressing that gap by examining how winter weather affects where crashes occur. Why winter-related crash analysis matters. Research by Kahn and others shows that rain, snow, and fog create unique crash clusters that differ from general crash patterns. Their findings highlight that weather-sensitive analysis are essential to understanding how environmental factors influence crash risk. As Kahn and colleagues note, this type of research provides an important first step toward localized analysis in identifying specific road segments or corridors that require weather-specific safety improvements. This creates an opportunity to explore whether Montgomery County has unique winter weather hotspots along its road network. The main goal was to determine whether freezing precipitation crashes form meaningful spatial clusters along the road network. Two key research questions guided the work. Do winter weather crashes cluster in statistically significant ways? Can network-constrained spatial analysis, such as network kernel density estimation, combined with network-constrained Geddes-Ord statistics, reliably detect these patterns? Traditional spatial statistics assume events occur across open and planar space, as shown to the image to the left, but traffic crashes occur along linear road networks, as shown on the image to the right. Researchers like Okabe and Yamada demonstrated that applying planar methods can create false positives, generating overestimations of clustering patterns. Network-constrained methods overcome this issue by analyzing crashes along the actual road geometry, leading to more accurate hotspot detection. Methods such as NKDE and G-links have significantly improved traffic analysis. NKDE smooths raw crash counts to highlight continuous density along roads, while G-links applies local spatial statistics to test significance. Studies by Z and Yan and me and others found that combining these two methods reduces false positives and reveals meaningful spatial clusters. This project integrates three main data sets: the Montgomery County crash reports, uh, ranging from 2015 to 2019, the Maryland AADT traffic volume dataset, and the county boundary. The crash data provides the event locations, weather conditions, and road conditions. AADT provides road traffic volume and the network. The boundary datasets ensures the analysis is limited to the correct jurisdiction. The analysis was limited to to this 5-year time window to align with the Vision Zero plan. To isolate winter weather crashes, I followed the Federal Highway Administration guidance as well as definitions used in prior research. Freezing precipitation crashes included events occurring during snow, sleet, freezing rain, and wintry mix, or when pavement was icy, snowy, or slushy. This ensured that I focused only on crashes most directly influenced by winter conditions while ensuring consistency with national standards. Network kernel density estimation creates a smooth crash density surface along the road network by spreading crash intensity within a defined bandwidth. This technique reduces random noise and highlights where weather-related crashes are most concentrated. Multiple Lixil lengths and bandwidth sizes were tested to evaluate result stability. Annual and 5-year NKDE services were created to assess stability with different sample sizes. G-links test whether a given road segment and its neighbors form a statistically significant hot or cold cluster. I used 99 Monte Carlo conditional permutations to estimate pseudo-significance levels, improving reliability and addressing assumptions about normality in density distributions. This step identified segments where a weather-related crash density was higher than expected by chance. These close-up images show a portion of Montgomery County, displaying the crash points, the corresponding NKDE surface, and the G-Links hotspot results. The orange dashed circles highlight locations where a single crash event produced a sharp density spike in the NKD output and was later flagged as a statistically significant hotspot in the G-Links results. To evaluate the stability of these patterns, multiple Lixil lengths and bandwidths were tested. Very short Lixils and small bandwidths exaggerated the influence of individual crashes, producing numerous false positive hotspots, while larger parameter values oversmoothed the network and obscured localized patterns. A balanced parameter set was selected from theoretical sizes used in previous studies to minimize these extremes. However, even with careful tuning, the results remain strongly influenced by data sparsity. Annual crash datasets were very small, approximately 140 to 220 crashes distributed across a long roadway network, causing NKDE to be dominated by single event density spikes. As a result, G-Links frequently identified these isolated spikes as statistically significant hotspots rather than true clusters. The 5-year data set increased the number of crashes and improved overall stability, but isolated event hotspots still appear, indicating that meaningful spatial clustering could not be reliably identified. This slide illustrates how study area size and crash volume influence the performance of NKDE and G-Links. The example on the left shows the Bowling Green, Kentucky study, which analyzed 3,226 crashes within a relatively small area of about 130 square kilometers. In that compact, dense urban setting, the results show no apparent false positive hotspots. In contrast, my study analyzed between 140 and 840 crashes across a much larger area of approximately 1,280 square kilometers. The example in the bottom right shows a study of Wuhan, China, which has a study area similar in size to Montgomery County, around 1,400 square kilometers, but with a much higher number of crashes, over 3,000 events. Despite the larger data set, the outputs still display false positive hotspots similar to those observed in my analysis, highlighted here with dashed orange circles. Together, these comparisons suggest that geographic extent itself plays a role in shaping NKDE and G-Link's results. In Montgomery County, the combination of a large road network and relatively few winter weather crashes produced density surfaces dominated by zero value segments. This caused NKDE to generate sharp density spikes at single crash locations, especially in areas with little surrounding activity. Because G-Links evaluates each segment relative to a very low global mean, these isolated events were often flagged as statistically significant hotspots. Data-driven bandwidth selection methods also struggled under these conditions, frequently recommending values that either exaggerated single events or oversmoothed the network. Overall, these results indicate that NKDE and G-Links are highly effective in dense, compact urban networks, but require adaptation when applied to large, sparsely populated county-scale datasets. The final conclusion is that no reliable or meaningful hotspots of freezing precipitation crashes could be identified. Instead, the project highlighted methodological limitations when using NKDE and G-Links with sparse and highly dispersed crash data. Future work could expand the dataset to include more years or use other weather-related crashes such as rain, focus on smaller urban areas, or develop adapted methods for low-density network events. Thank you for listening. This concludes my presentation. I'm happy to take any questions.
All right, Freddie, thanks. Great presentation.
Thank you.
We're waiting for a question to pop up in the chat window. How extensible could this be in terms of usability? In other words, how much did you struggle to identify the correct parameters for the NKDE, for example?
Well, so most of the studies, they were suggested type of bandwidths, a certain range of bandwidths to use that have shown positive results, and it was tested against other lixil sizes as well. Some of these studies, and so when I was trying them on my data set, they were quite difficult to tune, and so it was almost like an art. Like you have to kind of just make sure that you're not trying to use too big of lixil sizes to incorporate too many of the crashes where it doesn't catch the actual local spatial distribution of it. But you also don't want to make it too fine where you're getting all these spikes. But so I tried the theoretical side of it, but I also tried to do it with a data-driven approach, which I found through cross-validation, and I'm forgetting the other name of the other one at the moment, but that also struggled. One of them was saying a bandwidth of 50 feet, for example, and the other one was saying a bandwidth of greater um, than a mile, which wouldn't well, which wouldn't really help my analysis because I'm trying to find more at a local scale than it being at that large scale. So, if that answers your question.
Yeah, so there was a lot of, for lack of a better word, just guesswork in terms of trying the parameter and seeing what would result.
Correct. At that point, yes.
Looks like you have a question.
Studies like this look at and compare crash patterns. Correct. So there was some studies were done from the Vision Zero plan, and so those were looking at just I think all crashes, um, uh, and and so they were identifying the high injury corridors, and they didn't take this. I'm not sure exactly what analytical process they took. There was some results from the whole data analysis that they did. Um, and so with the and what this project was initially trying to do was to try to see if we could find these weather um, um, clusters and if they even differed from the ones that were shown on the study. But because uh, most of these lixels were being once the NKD was produced, it would create a lot of uh, um, zero density segments, which would influence the global mean when it was being calculated in the G-links calculations, and that's why we would see that. And I wasn't able to reliably determine if some of the hotspots that had more were actually true hotspots or not at that point.
All right. Well, thanks very much for your presentation, Freddie. If you could put your contact info in the chat window in case someone wants to follow up, that'd be great.
Okay, awesome. Thank you.
And then next up we have Joel. So,
Sorry, trying to find where to start.
okay, yep, thanks. So, Joel, if you want to go ahead and start sharing your screen, we can get your presentation set up. All right, we see your slides, so whenever you're ready, you can begin.
All right. Let me see real quick. Oh, it's not gonna work. Okay. Why is it not working? All right. We'll go based off of. Can you see my slides full or are they cut?
We see the PowerPoint interface.
Okay. So
But we were able to see the slide in its entirety. Yeah, you're good there.
okay. So good afternoon, everyone. My name is Joel Frick, and today I'll be presenting my research on evaluating the spatial association between crime patterns and transportation networks in Syracuse, New York. For the agenda, we'll be going over an introduction, the project goals and objectives, previous research, data and methodology, results, and then conclusion and questions at the very end. The purpose of this presentation is to explore where and when crimes are occurring in Syracuse, what types of crimes are most prevalent, and whether transportation networks like buses and highways have any impact on these crime patterns. To set the stage, in 2023, there were 14 million criminal offenses reported to the FBI across the United States. Of these, 6 million were property crimes, 4 million were larceny thefts, 1 million each for violent crimes and motor vehicle thefts, 884,550 for aggravated assaults, 839,563 burglaries, 227,795 robberies, 127,216 rapes, and 19,252 homicides. Focusing specifically on Syracuse, out of 100,000 residents, there were 626.8 assaults, 11.7 were murders, 55.1 were rapes, 197.7 were robberies, 806.6 were burglaries, and 1,815.7 were thefts, and 429.1 were motor vehicle thefts. Looking at the objectives and goals, the main objective of this project was to gather and analyze data on a range of crime types, including forgery, counterfeit, fraud, kidnapping, murder, possession or use of dangerous weapons, drug-related offenses, robbery, sale or manufacture of controlled substances, and arson over the last 4 years. In addition, we collected data on Syracuse transportation networks such as highways and buses. The key questions we sought to answer are: where are crimes occurring? Do they occur during specific months or seasons? Are transportation networks impacted by crime within the city? The ultimate goal is to share these findings with the Syracuse Police Department to support their ongoing efforts to address and resolve criminal issues in the community. For the previous research, prior studies show that identifying patterns and trends in crime data is challenging and requires careful analysis. Crime analysis involves both qualitative and quantitative approaches to better understand criminal behavior, reduce offenses, and evaluate police strategies. It's critical to know where to focus resources such as buildings, new police stations, or deploying more officers, and to identify areas where crime is most prevalent. Research highlights the need for data mining techniques for collection, classification, pattern recognition, predictive analysis, and visualization. Once data mining is complete, spatial mapping can reveal hotspots, monitor police initiatives, and provide deeper insights into criminal activities. Other studies emphasize the use of technology like CCTV and the breakdown of crime analysis into investigative, intelligence, tactical, strategic, and administrative categories. Importantly, research also points out that a significant number of crimes occur near transportation hubs, with people often targeted while walking to accessing buses or highway. For example, the upgrade of Carousel Mall to Destiny USA was associated with a notable increase in crime. These findings underscore the need to investigate the relationship between crimes and transportation networks in Syracuse. For the data and methodology for this project, we used multiple data sources, including crime data from the police department, boundary shapeouts, transportation network information, such as bus routes and highways, GTFS, bus stop locations, and combined Excel documents. Our methodology includes several steps: data mining to extract and organize crime information, combining DBF files to create a comprehensive data set in Excel, utilizing ARC Toolbox for 820 analysis and hotspot kernel density analysis, conducting Euclidean distance around transportation networks to assess proximity of crimes to highways and bus routes, using Tableau for data visualization, which enabled mapping of crime incidents and examination of trends over 4 years. This methodological framework allowed us to examine the spatial relationship between crime events and transportation infrastructure in Syracuse, New York. Looking at the actual results, you can see from the most active to the lowest active, Syracuse is divided into several different categories. It's categorized into north, east, south, and west. They classify each individual by north side, west side, east side, whatever, and then south side. Most of the impact is up near the north side and the east side once conducting the hotspot analysis. When we looked at 820 analysis, again, it looked at the primarily in the northern and the eastern, or the western side of Syracuse, New York. When we looked at the Tableau, there was a high increase of robberies within the July and September time period. And this was for 2021. When we looked at 2022, again, it's still consistent where the northern area of the kernel density and the western area had the highest activity. And then again, the 820 analysis provided the same results of where it was the northern and western side of Syracuse, New York. This showed that the possession and use of dangerous weapons, there was a peak in the April-June period. So it's appearing as though once we look at the 2023, again, similar outcomes. And again, looking at Tableau, Tableau provides information showing that possession and use of drugs is heightened in the July-September time period, and the possession and use of dangerous weapons, again, is still heightened in the July-September time period. Lastly, looking at 2024, it still has remained consistent where the northern region north side of Syracuse has remained the hotspot, and the western side is still remaining pretty consistent with the hotspot analysis. And it's getting more sporadic when it comes to criminal activity throughout the Syracuse, New York area for 2024. Again, when we look at the Tableau analysis, it's showing that most activity seems to be occurring between the April to September time period, where burglaries are starting to peak during the April time period. Possession or dangerous use of weapons seems to be peaking around the July to September time period. Our analysis identified several crime hotspots throughout Syracuse, many of which are closely associated with the city's main transportation networks. The results indicate that certain types of crimes are more likely to occur near bus routes and highways, especially in areas with high pedestrian activity. Seasonal and monthly patterns also emerged, with some crime types peaking during specific times of the year. By overlaying crime data with transportation network maps, we found clear evidence that proximity to transit corridors is a factor in the spatial distribution of offenses. This information is vital for law enforcement and city planners as they consider resource and allocation and crime prevention strategies. In summary, this research provides a comprehensive framework for analyzing criminal activity and its association with transportation networks in Syracuse. The hotspot analysis and spatial evaluation have revealed important patterns that can inform policing and public safety initiatives. As the next steps, we plan to develop an interactive dashboard allowing users to explore crime data by type, view annual trends, and examine specific incident locations on maps. Overall, our findings can help guide decision-making for the Syracuse Police Department and city officials, ultimately contributing to safer communities throughout the region. Thank you for your attention. I'm happy to take any questions you may have about the research, our methods, or findings presented today.
All right, Joel, thanks for your presentation. Great job. While we wait for a question to pop up, I wanted to get your thoughts on, because you'd mentioned that you included the bus lines and so forth. What kind of analysis or what kind of association do you think there would be with regards to, I know you probably weren't able to get this, but ridership at different bus stops. So you'd have a range of ridership numbers that occur across bus stops throughout the city.
So I couldn't get them. The only thing I could get is that was the GTFS file, was the actual bus stop locations. And that's how I was able to do the proximity analysis. Um, but the GTFS what came in a CVS file, and I had to import it and into a shapefile from the CVS file, and then do a distance based on it. But it didn't provide a lot of information based on like who rode the bus, numbers for bus routes, or any of that type of information.
All right. Thanks. Looks like you've got two questions in the chat window.
Try and see over.
And if you could read the questions before answering.
Okay, so how are you tying seasonal variations in crime to influence the transportation on crime? It seems like your research simply shows that crime is tied to proximity to certain transportation routes. So the way that I was able to do it is the data that I received from the police open data source showed time of year. It actually shows specifically all the way down to actually time of day, the day, the actual time that the incident occurred, and the year that the incident occurred. So what I was able to do is I was able to go into Tableau and query out that information to specify which specific crimes were occurring during which season. And then I wasn't able to do it on the densities. The only way that I would have been able to do it on the densities is by querying out based on what Tableau was displaying, querying out each individual incident based on that time of year, and then doing a hotspot analysis based on that specific information. If that answers your question on that one.
And we have another question there from
Yeah, would you say this study examined the impact of crime on transportation or the influence of transportation routes on criminal activity? I would like to say that from what I would say that it was more of an impact of crime on transportation networks. What I would like to see in that, what I would like to further investigate, is if it changed the timing of the transportation network to see if there was any adjustments with the actual timing at specific bus stop locations to see if they changed the timing based on criminal activity within that specific area.
All right. Well, thanks for your responses. And if you could put your contact info in the chat window in case anyone wants to follow up, that'd be great.
Okay.
Next up, we have Laura. So, Laura, if you want to go ahead and start sharing your screen, we can get you set up for your talk. All right, we see your presentation.
Okay.
You can start whenever you're ready.
Is my volume okay?
Yep, we can hear you.
Okay. My name is Laura, and I'll be presenting my capstone proposal project for 596A on modeling current and future suitable habitat of endangered fireflies in Florida. So I just want to start by giving an introduction to fireflies in general. They're actually a bioluminescent beetle. And because of that, they're unique and they're fascinating for people to watch. And they've been described by people, including scientists, as beloved, charismatic, iconic, and enchanting insects. For a lot of people, they invoke a feeling of nostalgia also. They've been celebrated for hundreds of years, if not longer, in folklore, art, and literature. And they also provide some economies around the world with ecotourism money. There's even firefly festivals that are held all over the world every year. They are they've been used in biomedical research, and they've helped scientists be able to develop a synthetic version of their light-producing enzyme luciferase to light up like body scans to look for abnormalities and diseases in the body. And they also use the light to light up contaminants in food. They're a major part of the food chain as a predator of snails and slugs and other soft-bodied invertebrates, and they're prey for spiders, birds, reptiles. And they use their light to warn predators, as well as for communication and finding mates. Their universal appeal makes them a good flagship species, which means they're popular with the public. They have public appeal, so they can be used kind of like as a symbol to raise awareness and advocate for conservation of their species and the species they live with and their associated habitats. And they're also a bioindicator species, so they're sensitive to pollution and changes in their habitat. And so their presence indicates good environmental health, and their absence may signal pollution or some kind of negative change in the environment. They have been in declining globally. People started realizing it before researchers did, and they kept asking, where have all the fireflies gone? There's a lot of my mainstream media articles about where are all the fireflies. And so then scientists started to look into it, and they found that there indeed has been a global decline. But there's also been a rise in recent years in the global conservation efforts by different international organizations, entomological organizations, specifically Xerces Society, and also even like the IUCN established a firefly specialist group. Since I'll be focusing on habitat suitability modeling, I am going to talk a little bit about firefly habitat in general, and then specifically Florida coastal habitat, because my study area is the coastal areas of Florida. So for most species of fireflies, they can be cold or warm climate species. In the cold climates, like in the north, they can like hibernate over the winter, and they live in forests, especially like in tree bark or under leaf litter. They like tall grasses, and all fireflies need to be like either near water or in a humid climate. Water is the most important factor for their habitat. And there's different species of fireflies that some are nocturnal and some are daytime. So obviously the nocturnal ones need darkness in order to flash and glow so they can find mates and communicate in that way. So Florida coastal firefly habitat, those fireflies are habitat specialists, meaning that they have limited habitat, limited food sources, and they're more at risk for extinction or threats to their habitat because of that. They live in salt marshes and mangroves mainly, and sometimes specific types of salt grass, or in sometimes upland areas where there's brackish water or upland type of vegetation. Florida's warm and humid, so obviously that's the climate that they prefer is warm, humid climate, and the larvae prey on intertidal snails. So snails that live they burrow like under the sand. So they need that as larvae to survive. So they are like an intertidal specialist, habitat specialist. And all around the world, fireflies are threatened by things like development and deforestation, pollution, and Florida coastal habitat is mostly threatened by land use change, specifically development, and then in turn, light pollution, and also by climate change, especially sea level rise. And when you have the ocean, like on one side coming on shore, and then you have development right along getting closer to the coast, you get what they call a coastal squeeze, which can lead to habitat loss, degradation, and fragmentation. These are, well, there's over 50 species of fireflies in Florida. They live all over the state, found in different habitats. 5 of them are listed as endangered, and 2 of those endangered species are these ones here, the Florida intertidal and the keel-necked fireflies. And I decided to focus on these, the habitat for these 2 species because they are similar species. They co-occur together. They're both endangered. They're both listed on the IUCN's red list, and they live in the same habitat. They have the same, they're both nocturnal. They're both flashing fireflies, and they both emit light in all 4 stages of their life as eggs, as larvae under the ground, under the sand, and then in their metamorphosis into adult stage, they also glow, and then they flash as adults. So according to the literature from firefly experts, almost the entire coastal region of the whole state of Florida is in need of research in on these fireflies and their habitat in order to try to conserve what is left of both. So sorry. My research question is where is potential current and future suitable habitat for these 2 fireflies? And my goal is going to be to develop a habitat suitability model to predict current and future potential suitable habitat, and then to calculate the potential habitat loss due to sea level rise. Habitats, a little bit about habitat suitability modeling. It's researchers are lacking observation data and habitat maps for these fireflies. I haven't come across any habitat maps in my search for relevant data because to describe a habitat as a land cover type only doesn't take into consideration other requirements like climate or pollution. So fortunately now there's new data and technology to help model habitat suitability. And we can do that by using different algorithms that can associate observation data with environmental conditions at the observation locations to help predict other potential current suitable habitat in your study area. And then you can also add future climate and future land use data to predict areas of potential future suitable habitat. And these habitat maps can help determine locations for these researchers to do surveys to find more of the fireflies and for habitat conservation efforts. Some relevant literature, I chose 3 publications, one by Stephen Phillips. He's the main developer of the MaxEnt modeling technique for species geographic distributions and predicted suitability of habitat. So he yeah, so he's he's the one that developed the machine learning technique called maximum entropy modeling. And that's what I'm going to be using within ArcGIS for my project. The second one is a publication that was written by many of the firefly experts out there on their life history and habitat associations and threats to them and their habitat. Also, they provide guidelines for conservation that they advocate for people to even provide firefly habitat like in their backyards and everything. Then the third one is an example of using the MaxEnt model for habitat suitability for rare fireflies in a coastal region with limited observation data, which is very similar to my background and my methods and my available data. So that's one that I can use as a model as I'm doing my project. I want to introduce the study area and give an idea on what the observation data looks like. The red and purple dots along the coasts of Florida there represent observations. The light blue areas up at the northern part represent saltgrass, and the bright green areas represent mangroves. The 2 smaller images are just those 2, the Big Bend area and then the Everglades area zoomed in, so you can see that in the north is more saltgrass, in the south there's a lot of mangroves. So those are big habitat areas for these fireflies. And you can see that there isn't a lot of available habitat in the whole state, and there isn't a lot of observation data. So, but my goal is going to be to model the habitat using the environmental conditions at those observation point locations to predict other potential areas of suitable habitat. And the proposed methods are going to be for me to use the MaxEnt presence only prediction model in ArcGIS Pro and then to overlay sea level rise. So I will first just need to prepare my my observation data. Then choose appropriate environmental conditions that represent the 2 fireflies' habitat requirements. And those will be the model's training variables, the inputs. And then I'll input that data into the MaxEnt tool in ArcGIS Pro, and then evaluate the training outputs and response curves. And then I'll work on eliminating some of the variables that are similar to each other and continue to refine and build a model of habitat suitability. And once I'm happy with the results, I can evaluate the final model with goodness of fit metrics and evaluate the final response curves, and then apply the model to predict current and future habitat suitability. And then I would also like to overlay different intervals of sea level rise on the habitat and calculate the area of potential loss of habitat due to sea level rise. And this is the data that I intend to use, observation points. And I put a little image of what the data looks like: land cover, land use, bioclimatic and climate data, so like temperature and precipitation. And I'm going to use the VIIRS nighttime lights from NASA to use that as to show like light pollution areas. And those will go into the model, and then sea level rise will be an extra step outside of the model. And then I also wanted to consider using other data in the model, like soil elevation, and then future land use, and maybe overlay protected areas on the final results. And this is just shows a little bit more detail of the Maxent model, the inputs and outputs for it. The inputs are the data layers, and then parameters that I set to build the model. And then the outputs are going to be response curves for each environmental variable. I will need to evaluate all of them to find the ones that best represent what we know of the species habitat requirements. And this example shows the probability of species presence across the range of values for the variable minimum temperature of the coldest month. So it shows as the temperatures in the coldest months increase, so does the probability of presence, which is true. So that's a good response curve to use in my final model, a good environmental variable to use in my final model. And the other model output is the map of the probability of suitable habitat. And so the darker areas represent a higher probability. And then for sea level rise, I intend to use NOAA's sea level rise extent rasters, which I'll have to download and mosaic for the whole state of Florida. And then overlay those on, well, then I'll create a binary raster of suitable, non-suitable habitat, and then overlay the sea level rise on the suitable habitat areas and calculate the potential loss of suitable habitat to sea level rise. And the anticipated results, so it's going to be my binary raster of suitable, non-suitable habitat, and then a table showing the percent of the total area of the whole state that is current suitable and then future suitable habitat, and then a table of the percent of suitable habitat loss due to a sea level rise of 1 and 3 feet for the whole state. And then for my my timeline and possible presentation venues, I have my timeline is going to be to take 596B in the summer, write up my final proposal and my final presentation, and then some conference ideas that we came up with so far are these ones listed here. I'm gonna look out and see what the abstracts are due, and I have to write an abstract before I do any of that, and then I can submit those to some conferences and hopefully get that done next summer. And my references, and that's it. And then any questions, I'll take.
All right, Laura, thanks so much. Great, great presentation. While we're waiting for questions to show up, I'll ask you a question. So with the observation data, like with bird counts, they can actually count, the number of birds. Does the observation data that you have access to, is it just a point data saying, yes, they were here, or is there an estimate of the numbers of fireflies at a given location?
They have both, but I'm not going to use the estimate of numbers. I'm just going to use the ones that they say that they were here, because I don't want duplicates in the same area. I don't think that would be helpful for what I'm doing. I'm not looking to like calculate abundance or anything like that. I'm just looking to mostly model the habitat of where they're found. So I just want to use the observation data of where they definitely have been found, and that the observations have been verified by experts, because there's not very many of these observations for these fireflies since they're endangered. So does that answer? I hope that answers your question.
Yeah, so it's just a coordinate value, or is it a polygon?
I'm sorry?
Is the location, is it expressed as a coordinate, like a
Oh, yeah,
centroid, or is it
yes.
or a polygon?
Yes, they're coordinate points.
Okay, all right. Okay. Looks like you have a question in the chat window.
Okay. Cool topic. It seems like you have a fairly small number of observations. Would it make sense to expand the species? I think you said Florida has approximately 50. You're looking at to increase the observations. So I know it has, there's a very small number of observations and that was one of my challenges for this whole project was trying to find a region that had enough species to do this modeling. And I'm not sure if these are even enough, but there has been research out there where there's been very few observations used in species distribution models that I'm gonna kind of go by. And they say that that max ent can be a good model to use with just a small number of observations. So, and can't I can't really expand the species in Florida because the other species of fireflies, they don't necessarily live along the coasts. So these ones are specifically coastal fireflies and they're rare and they're endangered and I know the experts are looking for uh other areas to find them and so I thought that this hopefully maybe I'll be able to contribute something to the field with this information because it's hard for them to um, find these fireflies and it's hard for them to know where else to look.
All right. Well, thanks for your response. Why don't you go ahead and put your contact info in the chat window, and then when they
Okay.
have a follow-up question, they can let you know. And with that, I believe we have come to the conclusion of today's capstone presentations. So I want to again thank all the presenters, did a great job. I appreciate the audience and the questions. We have another session tomorrow at the same time. We've got another slate of capstone presentations. So if you would mark that on a calendar, we will start at 11:30 Eastern, and I hope to see you there. Have a good day.